just to keep it consistent. So first off was the urinary system chapter, chapter 26. What were the functions of the urinary system?
Filtration.
Yeah, like filtering your blood, right? Go ahead, Corey. What are you saying?
I was gonna say like regulate blood volume.
Waste.
Regulate blood volume, get rid of waste products, right? Like urea, for example, which is a nitrogenous waste, but regulating like sodium chloride levels, regulating total water balance. Don't forget, it's also the source of two hormones. What are the two hormones that come from the kidney? Renin and EPO, right? What's renin do?
Helps with the blood pressure.
Yeah, ultimately it's going to do what to your blood pressure? Increase it, right? And then what does EPO do?
Urinary.
It causes you to make red blood cells, right? In terms of the anatomy, what's the outer part of the kidney called? Well, not the capsule, but the cortex, right? And then the middle part's called the medulla. If you look at the medulla, what's the triangular things in the medulla? Pyramids, and then separating those are the renal columns. Good. Does the kidney have good blood flow?
Yes.
Yeah, it has. And let's go through it then. So, what's the main vessels that bring blood into the kidney? Renal arteries, which are branches off of what? Well, hold on. The renal arteries are branches off of what? The aorta, the abdominal aorta. Then from the renal arteries, you go to the segmental. Then what? Interlobar. Then arcuate, right? Then what?
The
Cortico-radiate arteries. Then what?
Into the afferent.
You go to the afferent arterial. Then
the glomerulus.
glomerulus. Then you go to the efferent arterial. Then you go to the peritubular capillaries. And if you're in a juxtamedullary nephron, what else do you have there? You have the vasa recta. Then you go into the peritubular venules. Then you go into the, kind of going backwards now, cortico-radiate veins. Then you go into the arcuate vein, then into the interlobar vein, then into the, and this is where it kind of breaks up. Sometimes you go into a segmental vein, sometimes you go directly into a renal vein, and then eventually where does all the blood go back into?
It's inferior vena cava.
Inferior vena cava, right?
Inferior.
All right. What's the name of the functional unit of the kidney? Nephron. And what are the two kind of areas to the nephron, or the parts of the nephron? The corpuscle and the tubules, right? If you look at the renal corpuscle, what's the name of the blood vessels on the inside? Glomerulus, or you can call them glomerular capillaries. And then what's surrounding that? Bowman's capsule. Now, if you look at Bowman's capsule, there's two layers to it. What's the name of the layer that's directly attached to the capillaries? That's the visceral layer. Then you have the space, which is Bowman's space, and then what's the layer that's on the outside? The parietal layer. If you look at the visceral layer, what's the name of the weird-looking cells that make up the visceral layer? Podocytes, which translates into like feet cells, right? What process of urine formation happens at the renal corpuscle? I'll give you a hint. It's the first process. Filtration. And so, in order to do that, we'll talk about it later. But you gotta force liquid and other substances out of your blood through that filtration membrane into Bowman's space. The filtration membrane itself is made up of the endothelial layer of the glomerulus. And what kind of a capillary is the glomerulus categorized as? Fenestrated capillary. Then you have the joined basement membranes, which is referred to as the basal lamina. And then you have the visceral layer of Bowman's capsule, specifically what's called the slit membrane that kind of runs in between them. So that makes up the filtration membrane. Do most things pass through the filtration membrane? Yes. Most things pass through the filtration membrane pretty easily, with the exception of what? Who doesn't get through the filtration membrane? So medium and large size proteins don't get through. Pretty much everything else, including small proteins, can actually pass through the filtration membrane. Now let's talk about the urine flow. So we talked about the blood flow. Let's talk about the urine flow. So first urine, the filtrate shows up in Bowman's space. Then where does it go?
The
Proximal convoluted tubule, PCT. Then you go into the descending limb of the family, then the ascending limb, then into the DCT, then into the collecting duct, then into the papillary duct, then out through the papilla, then it's caught by a mitocalyx, which then combines to form a major calyx, which dumps into the renal pelvis, which is connected to the ureter, which then goes to the bladder, and then out through the urethra. All right, good, you got it. Where is this thing? Okay. What are the two types of nephrons you have? Juxtamedullary and cortical. Which one is more common? Cortical, right? 80 to 85%, 15 to 20% are juxtamedullary. Let's talk about the physiology then. So what are the three processes that go on in urine formation? The first step is always what?
Glomerular filtration.
Glomerular filtration, and then what are the other two things?
Tubular reabsorption.
Tubular reabsorption and tubular secretion. So during filtration, it's basically different pressures are acting on the blood and the glomerulus to force the fluid and other substances through that filtration membrane and into Bowman space. We'll talk more about that in a second. What happens during reabsorption? You're essentially doing what? Is this a tough one? You guys were so great at everything that it's like crickets now. Reabsorption is bringing stuff back in that you didn't really want to get rid of. Things that might be in that preliminary urine that you really didn't want to get rid of, that's reabsorption. And then what's secretion?
Getting rid of waste.
So getting rid of wastes that couldn't make it through the filtration step, but that you still want to get rid of, right? All right. Let's talk about the filtration then in more detail. So filtration is basically just the same thing as capillary exchange that you learned about in the blood vessel chapter, okay? It's governed by different hydrostatic and different osmotic pressures, right? What's the main pressure that's forcing fluid out of the glomerulus and into Bowman space? The glomerular blood hydrostatic pressure, that's the main pressure that's moving in that direction. And then going against that, what are the two pressures that go against that? Capsular hydrostatic pressure and the blood colloid osmotic pressure. So if you take those two guys and add them together and subtract them from the glomerular blood hydrostatic pressure, what's the value that you should get? 10 millimeters of mercury. The fact that it's positive value tells you what?
Everything's working.
Everything's working, you're making urine, right? And that's a good thing, okay? All right. Now, you can measure what's called the glomerular filtration rate. That's basically how quickly you're making filtrate each minute. What was the normal value for men?
125.
125, and what was it for women?
105.
105. Remember, in order for you to be in homeostasis, to make sure that you're getting rid of the waste products that you need to be, etc., you need to keep those values pretty close to those numbers, okay? And there were three mechanisms in place that helped to control your glomerular filtration rate. What were the three mechanisms? Renal autoregulation, neuroregulation, and hormonal regulation. Speaking of hormonal regulation, what were the two hormones that influenced the GFR? Atrial natriuretic peptide and angiotensin 2. What did atrial natriuretic peptide do to the glomerular filtration rate? Increase or decrease it? Increases it. How? By relaxing little bits of smooth muscle that are in the wall of the glomerulus. And what that does is that'll let the glomerulus spread out. That will increase the surface area and allow more filtration to happen. And that'll increase the glomerular filtration rate. And what did angiotensin 2 do to the glomerular filtration rate? Decrease it. How is it decreasing it? By basically constricting the arterioles, especially the afferent arteriole. When that's constricted, less blood flows into the glomerulus, which reduces the glomerular blood hydrostatic pressure. A lower glomerular blood hydrostatic pressure means less filtration takes place and the GFR goes down. Okay? Reabsorption. True or false? Most of the filtrate gets reabsorbed. True. What percentage of the filtrate gets reabsorbed? 99%, so almost all of it. And where in the nephron is the majority of that reabsorption happening? in the proximal convoluted tubule. Okay, what percentage or what fraction of reabsorption happened in the PCT?
Oh, 2/3.
2/3, or like 65 or 66% of the reabsorption is happening in the PCT. Now, when reabsorption happens, things can get reabsorbed either between tubule cells or directly through tubule cells. What's it called when you get reabsorbed directly through tubular cells?
Parasite.
That's called transcellular reabsorption. See, I went out of order there just to throw you off. And what's it called when you sneak in between the cells? Paracellular reabsorption. Good. Another distinction in how you do reabsorption is whether you do active transport or passive transport. What does active transport mean?
ATP.
You need energy to make it happen. It may be in the form of ATP or it may be in some other form. And then what does passive mean? No energy is needed because it's based on diffusion, right? The natural process of diffusion. As for water reabsorption, remember there's obligatory and there's facultative water reabsorption. What does obligatory water reabsorption mean?
Water has to be reabsorbed.
It means it has to be reabsorbed to basically follow the solutes that are being reabsorbed to maintain the osmotic gradients, right? And what does facultative mean?
It's based on specific needs.
And you can adjust it, right? You have control over facultative water reabsorption. If you're looking at the nephron, most of the early reabsorption in the PCT, the descending limb, that's going to be obligatory reabsorption. But then when you move towards the end of the nephron, like the DCT or the collecting duct, that's where you have facultative reabsorption. What are the two hormones that influence facultative reabsorption? ADH and aldosterone. Good. And then we have tubular secretion. Again, tubular secretion is the way to get rid of materials that maybe couldn't make it through the filtration step. Filtration is also an important, or excuse me, secretion is also an important step for controlling the pH by adjusting how much hydrogen is being secreted. All right, moving right along. Hormonal control of reabsorption. Let's go through RAS again because I want to beat you down with this. So, what's the first thing in RAS that gets released? Renin. And what triggers RAS?
Low blood pressure.
Low blood pressure. So and who releases the renin? The kidneys, specifically what cells? Rhymes with buxtoglomerular cells. The juxtaglomerular cells, they release the renin. And what does renin do? Converts angiotensinogen into angiotensin 1. Angiotensin 1 then goes to where? Lungs, gets converted into angiotensin 2 by what enzyme? ACE, angiotensin converting enzyme. What's the group of drugs that work on ACE called? ACE inhibitors, and what do they use to treat? High blood pressure, okay? Do you know how you can tell an ACE inhibitor by looking at the name? They usually end in the letters IL, so like Acupril or Lisinopril. If it ends in IL, it usually is a ACE inhibitor. Okay, and then what happens? So let's suppose then you have the angiotensin 2. What does it do that directly helps to raise your blood pressure? It's a widespread vasoconstrictor, okay? That in and of itself is going to help to raise your blood pressure. But in addition, what else does angiotensin 2 do that helps? It goes to the cortex of the adrenal gland and causes aldosterone to be released, which then causes sodium chloride plus water reabsorption. That increases your blood volume, which increases your blood pressure. The other thing to remember about aldosterone is, while it's causing sodium and chloride reabsorption, it's at the same time causing you to secrete what?
More potassium.
More potassium. So you can bypass the whole silly RAS thing if you have what problem? Hyperkalemia. And aldosterone will help to get the potassium out of your body. Okay. Formation of dilute and concentrated urine. What is the main hormone that determines whether your urine is dilute or concentrated? ADH. If you're dehydrated, will you or will you not release ADH? You will, right? And if you release ADH, what will your urine look like? It'll be very concentrated. It'll be like, you know, dark yellow, brownish, right? It'll be very concentrated. How, from a very specific level, how does ADH actually cause water reabsorption? By putting what in place? By putting little water channels called aquaporins in place that allow the water to be reabsorbed, right? When would you not want to release ADH?
When you're dehydrated.
When you're what?
Dehydrated?
When you're hydrated.
Oh, you're
When you're
hydrated.
overly hydrated, you don't want to release ADH, right? Because you want to pee that extra water out. So when you've got too much water on board, don't release ADH. What will the urine look like?
Clear.
Very dilute, very clear, high water content, you know, high volumes, all that stuff. All right. Evaluation of kidney function. How much urine output should you typically have on a normal day?
1 to 2 liters.
1 to 2 liters. Water. Wow, just messed it up. Urine's mostly what?
Water.
Water. 95% water. What's responsible for the coloration of the urine? Bilirubin, which ultimately came from where? The breakdown of red blood cells and hemoglobin that's inside of them, right? Remember, bilirubin is also responsible for the color of the bile, color of the stool, and the nasty yellow color you get like on bruises, right? In terms of evaluating kidney function, what are probably the 2 most common blood tests that you use to evaluate kidney function? The BUN and creatinine, okay? BUN is based on nitrogen waste in the blood. It comes from breaking down amino acids. Creatinine comes from breaking down creatine phosphate and skeletal muscle. If either one of those go up, it's usually a sign that there's a problem with your kidneys. Okay. After the kidneys come the ureters. What makes urine move through the ureters? Well, first of all, it's just pressure. It's hydrostatic pressure, okay? As more urine's made, it increases the hydrostatic pressure inside of the ureters, which then obviously pushes the urine along, right? So it's that. It's also gravity, right? Standing up or sitting, it's easier for the urine to flow from your kidneys down to your bladder, right? And then also, too, don't forget, there is muscle in the wall of the ureter that can contract to do peristalsis to move it along, right? What direction is the inner muscular layer? Longitudinal, and the outer layer is circular, which is just the inverse from like your intestines, right? All right. Now, if you look inside the bladder, the spot where the 2 ureters come in, and then the spot where the urethra leaves, if you connect that, you form this kind of triangular shaped area called the what? Trigone. Again, there is a built-in urination reflex. By the way, what's the fancy name for urination? Micturition, right? If you ever volunteer at a hospital and there's a micturition lab, just know that that means the same thing as the urination lab. In terms of the reflex, it's the parasympathetic system that promotes urination, causes contraction of, what's the name of the muscle that's in the wall of the bladder? The detrusor muscle, and it also promotes relaxation of the internal urethral sphincter. When you're an embryo, which of the 3 layers in an embryo did the kidneys come from? Mesoderm. All right, enough said. Moving right along, chapter 27, fluid electrolyte and acid-base homeostasis. So remember you have these, no, that comes up later. Don't remember that yet, sorry. How much water do you have in your body? A lot. What percentage?
45 to 75.
45 to 75, right?
Is a lot not gonna be in one of the answer blocks?
What's that?
Is a lot not going to be one
That's
of the
not
answer
gonna be
blocks?
one of the ones. No, I'm not gonna. No more slow pitches. No more smoking is bad for you.
That's
This is
hilarious.
this is all tough stuff now. Yeah, you guys have proven yourself. You're ready for the next level. So,
Screw that.
who's up at like 75% water or even higher? Newborns, right? And then who's down at like 45% or even lower?
Old people.
Old, dried up, old, crusty,
Little raisins.
desiccated
Little
bacon like
raisins.
in old people. Nary a drop of water on them. They're like the Sahara Desert.
Beef jerky.
Maybe I might be belaboring the point a bit much. Anyway, moving on. I got all distracted there. What are the two main body compartments?
Intracellular.
Intracellular and extracellular. Are there any subdivisions for the intracellular? Do you subdivide intracellular water usually? No, you just call it intracellular water. You don't be like intramitochondrial water, you don't. But you do subdivide extracellular. What are the two main divisions of extracellular? Corey, don't anyone else answer. Corey.
In your tissues and then in your blood plasma.
That's right. So the interstitial fluid and then the plasma, right? Where do you have more fluid, intracellular or extracellular? Intracellular. So like 2/3 is intracellular, 1/3 is extracellular. And then of the extracellular, what fraction or what percentage is interstitial and what fraction or percentage is plasma?
20% plasma.
Go ahead.
80%.
Corey's over here being polite, Jess, and you just ran right through with the answer. Sorry, Corey, I didn't hear what he said. Go ahead.
It's okay. I think it's 80% in the tissues, 20% in the plasma.
That's right. Good for you.
Good for him.
Ugh. I wish the good manners that you have would just kind of diffuse into your neighbors over there at that other table. Ugh. You're such beasts over there. All right. I'm cracking myself. I love it when I'm my biggest fan. Okay, so moving on here. Water balance in the body. What's the main way that water gets into your system? Through your mouth, right? Through the foods that you eat or the drinks that you drink, right? Roughly 2,300 milliliters per day, give or take, right, is coming in through your mouth. But that's not the only way. What's the other way that water gets into your system? Go ahead. You don't have to. Go ahead. You don't have to.
Metabolism?
Yeah, metabolism, right? Remember at the very end of cellular respiration, you create metabolic water, right? As oxygen accepts the hydrogens and the electrons, you create, how much of that water are you making on a daily basis? About 200 milliliters, right? What's the main way that water gets out of your system? Your kidneys, right? Again, somewhere around 1,500 milliliters, 1 to 2 liters per day, whatever. But you also lose water through your skin, through your lungs when you breathe out water vapor, and then also in your stool. How much water should be in your stool? 100 milliliters. In terms of regulating water intake, there is a thirst center. Where's that located? Hypothalamus. And when water loss is greater than water gain, you become dehydrated. And then, by having a dry mouth and decreased saliva, or by stimulating osmoreceptors, all of those things will feed in and kind of stimulate this thirst center, and hopefully then you'll be able to find something to drink. Regulation of water and solute loss. Regulating sodium chloride loss is the main way that you determine your body fluid volume, and that's the main way that aldosterone acts, okay? Aldosterone is moving solute and solvent at the same time. Aldosterone is causing you to retain sodium and chloride, which is the solute, but it's also causing you to retain water, which is the solvent. When you're moving solute and solvent at the same time, you'll change body fluid volumes, but you won't change body fluid concentrations per se. If you just move one of those components, like just the water part of it, that's when you'll actually change the concentration, and that's exactly how ADH works, right? So a little bit difference there. What's the hormone that you want to release when you want to decrease your blood pressure? Is that a tough one too? ANP, atrial natriuretic peptide. Atrial natriuretic peptide is kind of like just the opposite of aldosterone. It causes you to get rid of sodium chloride water follows, you decrease your blood volume, and that decreases your blood pressure. Okay. Back to ADH. Again, ADH changes the concentration of your urine, it changes the concentration of your blood because it's just moving the water component without affecting sodium and chloride. What's the other name for ADH? Vasopressin. And where does it come from in your body? Posterior pituitary. Good. What else comes from the posterior pituitary?
I'm not saying.
Sebastian, he raised his hand.
It's spreading.
Do you go home at night and just get like angry at all these people around you, like I'm gonna get them or anything like that? You like seethe?
A little bit.
Yeah, I would. I'd be so. Yeah, I'd be really mad at him. I'd be so sore. All right. Electrolytes. Electrolytes are substances that give off ions when they dissolve, such as sodium chloride. 4 general functions for electrolytes in the body. They help control osmotic balance because they're more numerous than the non-electrolytes. They influence acid-base balance. They can carry electrical current, like the sodium and the potassium when you think about those moving through gated ion channels in your neurons. And then several of them act as cofactors that can turn on enzymes, such as calcium is great for turning on enzymes by attaching to it. Now, if you compare the different body compartments and the fluids that are in those compartments, do you see big differences in the type of fluid that you have in the plasma versus in the interstitial fluid? Is there a big difference between plasma and interstitial fluid? Not much, except for the fact that you have more what in the plasma than in interstitial fluid? More proteins, okay? Why are there so many proteins in the plasma? Who put them there? Give you a hint. It's a big organ in the right upper quadrant. The liver, right? There's a lot of proteins in plasma because the liver put them there. There's not that many proteins in the interstitial fluid. But aside from that, they're pretty similar. What about if you compare those two guys with the intracellular fluid? Are there big differences between the extracellular fluids and the intracellular fluids? Yeah, there's a lot of differences, right? For example, sodium. Where do you find lots of sodium? In the, which fluid? Well, or just the extracellular fluid in general, there's high amounts of sodium. Do you have that much sodium inside of your cells? No. What about potassium?
Yes.
It's just the opposite, right? Lots of potassium in the intracellular fluid, not that much potassium in the extracellular fluid. So big differences between those guys. Speaking of the specific electrolytes, let's go through some of these ions then. So sodium, you find it's the most abundant extracellular cation. Sodium is really important during neuron electrical signaling transmission. It's also important for setting up osmotic balance in the body. Chloride usually follows along with the sodium. It's the major extracellular anion. Potassium is the major intracellular cation. It's also important for electrical signaling that's going on there. Bicarbonate is the major anion that you find in your plasma. Why is there so much bicarbonate in the plasma?
It's the way it gets transferred.
That's the main way that CO2 is getting transported in the blood, right? All right, that's pretty good. Calcium, again, calcium is the most abundant mineral in the body. What does it mean to be a mineral?
Non-organic.
You gotta be, well, the word mineral, that's true. A mineral is non-organic, but mineral also means it's found where? In the Earth's crust, right? Phosphate, again, phosphate is often found in your bone, deposited along with calcium as these calcium phosphate salts. Parathyroid hormone and calcitriol are two hormones that influence both calcium and phosphate levels. In the case of PTH causes your kidneys to retain calcium, but it causes your kidneys to get rid of phosphate. In the case of calcitriol is just the other name for the active form of what? Vitamin D. Calcitriol actually causes both calcium and phosphate to be absorbed in your intestines. Magnesium is very similar to calcium in that it's a divalent cation, but the location is different. Calcium is usually extracellular, Magnesium is usually intracellular. Magnesium does a ton of important stuff. It's a good assister. For example, you need it to kind of keep the sodium potassium pump running. It's important for neuromuscular activity and myocardial functioning. It does a bunch of things. What kind of people are at risk for getting electrolyte imbalances? Those dependent on, healthcare providers, et cetera, for their fluid and electrolyte needs, right? People that are not taking food in normally through their mouth. Maybe they have a tube put in, like a nasogastric tube, and they have to be fed that way. Maybe they have, maybe they're not even getting food in their GI tract at all. Maybe they're getting total parenteral nutrition, where they're getting the food essentially in their veins, right? All of that can mess with their fluid electrolyte levels. Or at the other end, maybe they have special catheters in that are draining them, like they have a urinary catheter in, or they've had a procedure like a colostomy or an ileostomy, where they've had a portion of their intestines removed and the intestines attached to their skin. Anytime you mess with all those things, you run a good chance at causing an electrolyte imbalance. And in those people, when they're admitted to hospitals, it's very common to do what's called a Chem7 blood test on them, where you constantly measure sodium, potassium levels, chloride, BUN, creatinine, you're checking all that stuff, blood glucose levels, all that stuff. Next part of this was acid-base balance. What's the normal pH again for your blood? 7.35 to 7.45. Why do we even have a normal range? Why who cares? Why can't I just have a pH that I want to have? Why do I gotta have these normal ranges? Because you don't want to die, that's true. For homeostasis, okay, that's a very generic, and you can't be wrong, but you're never really right with that answer, yeah. So what, can you tell me in more detail, why do you need to have a pH within those various ranges? To keep who happy? The proteins. Proteins are very finicky about the pH, and it can change their shape. And if a protein loses its shape, what's that called? Denaturation. And when they lose their shape, they also lose their function, and then bad things start to happen and you can actually die from it. So that's why that's the big reason why you have these normal range for your pH, to make the proteins function. What are the three things that help keep your pH within its normal range? Buffers. We start out so strong. Buffers, then you're supposed to say two more things. So the lungs, and then also the kidneys. All right. Who amongst those three, buffers, kidneys, or lungs, acts the fastest? Well, the buffers act the fastest. All right. Buffers act within fractions of a second to basically correct your pH. Okay. Buffers are always made up of two chemicals, one that acts like a weak acid, and then one that acts like a weak base, and they quickly can convert stronger acids or stronger bases into weaker acids or weaker bases that don't disrupt your pH as much, right? So buffers, fast, fast, fast. Next, who's a little bit slower than the buffers? The lungs, okay? By adjusting how much CO2 you exhale, that will influence your pH. If you don't exhale enough CO2 builds up in your blood, and what happens to the pH of your blood? It becomes more acidic, okay? As CO2 builds up, your blood pH goes down, you become more acidic. If you get rid of too much CO2 from your lungs, the pH goes up and you become more alkaline, right? And then finally, the slowest to act is the kidneys, and they can make adjustments in terms of how much how much hydrogen and how much bicarbonate you're secreting or reabsorbing, right? Lungs can take a few minutes to kind of do their job. Kidneys can take hours to days to kind of make their adjustments. In terms of acid-base problems, what are the problems called if your pH is below 7.35? Acidosis. And if it's above 7.45? Alkalosis. If the problem lies with CO2 levels being too high or too low, what's that classified as?
Compensation.
Well, that's classified as a respiratory problem. And if it's a problem with bicarbonate levels being too high or too low, that's classified as metabolic, right? So you can mix and match these things, right? You can have a respiratory acidosis or a respiratory alkalosis or a metabolic acidosis or a metabolic alkalosis, right? All right, that's all I want to say about that, which then leaves us
Not bad, not bad.
with chapter 25. We're in the home stretch. Hang in there. We're almost done. All right, what's the definition of metabolism? Sum of all chemical reactions in the body. What's it called when you build things? Anabolic or anabolism. And when you break things down? Catabolic. In terms of energy, which type of reactions usually give off energy? Catabolic or anabolic?
Catabolic.
Yeah, usually when you break things down, it gives off energy. And what's the name for a reaction when it gives off energy? Exergonic. And then when you build things, those usually require energy, right? And what's that called when you require energy? Endergonic. Okay. And remember, the two often go together, right? You can use the energy that's released from a catabolic reaction to then provide the energy that's needed to make an anabolic reaction happen. Your body's favorite catabolic reaction for producing energy is breaking down ATP, right? Remember, those final two phosphate groups are kind of held on with these high energy bonds, right? And when you break off those phosphate groups, it releases energy. If you break off one phosphate group, what do you get? ADP. If you break off two phosphate groups, what do you get?
AMP.
AMP. All right. Now, when you make ATP, which we spent a lot of time talking about, that's when you break down glucose, and that's referred to as cellular respiration. And we're going to get into that in a moment. But most of the reactions that take place during cellular respiration are some form of what kinds of reactions? Redox reactions. What does redox stand for? Reduction and oxidation. What happens to a chemical that gets reduced? If it's reduced, it's getting what? It's gaining electrons. And if it's oxidized, it's losing electrons. Now, in addition to the electrons that are being gained and lost, what atom is usually also gained and lost at the same time? Hydrogen. So you end up having a hydrogen plus two electrons, and that forms what's called a hydride ion, right? All right, so fine. We'll move on. Okay, so let's talk about carb metabolism then. Again, when you break down glucose to form ATP, that's referred to as cellular respiration. If you want to get as much ATP as possible, what do you need to have around to break down the glucose? Oxygen. And what type of cellular respiration is that called?
That's aerobic.
That's aerobic cellular respiration. You got that? You can go through all the steps. You'll get as much ATP as possible. What organelle do you also need to make that happen? You got to have mitochondria for that to happen, right? If you don't have mitochondria or you don't have oxygen, then you're limited to doing what? Glycolysis, which is essentially what they call anaerobic respiration, right? So let's assume, though, that you do have oxygen, so you can go through the whole shebang, you get to do the whole thing. If you're starting with glucose and oxygen, those are kind of the inputs. At the end of the whole thing, what are the three things that you get out at the end of the whole thing? ATP, which is carbon dioxide as a waste product, and
Metabolic
water, metabolic water, okay? 4 kind of major steps to aerobic cellular respiration. What's the first step?
Deoxidized.
Glycolysis. What's the second step? It doesn't get as much publicity, but it's
The formation.
they sometimes call it the formation of acetyl-CoA, or they call it the transition step. What's the third step?
Krebs cycle.
Krebs cycle, also known as the citric acid cycle, also known as the,
There's another one?
Is it a rapper?
I didn't tell you guys this?
No.
Oh man, you did not get your money's worth. I totally told the class this morning. I hope you feel jealous. It was called the tricarboxylic acid cycle.
Forgot.
So yeah, I'm not following.
They gotta be here at the end.
There's going to be you know what? I'm going to go home tonight. I'm going to convert every question into that.
Into
It's all going to be about the tricarboxylic acid
That's how you
cycle.
didn't control the
That's
test.
it. I'm too infuriated now. The change is going to happen.
Conspiracy.
And then what's the last step?
Electron transport.
Electron transport chain or electron transport system. All right. So let's go through these in order then. So let's start with glycolysis. What do you start with glycolysis? Glucose. And what do you get at the very end? Not quite. You get pyruvic acid, right? How many pyruvic acids if you start with one glucose? 2. How many ATP do you make directly from glycolysis?
2, but technically 1.
You make 2 ATP directly from glycolysis, right? Or you could say 2 net ATP, right? Okay. On the test, if they ever ask you, and they might do this, wink, wink, if they ever ask you how many ATPs you get from glycolysis, you should say 2, okay? How did they get that number? Well, remember, there's 4 ATP being made in the final steps of glycolysis, but at one of the earlier steps, you required 2 ATP. So 4 minus 2 is what gives you 2, all right? So if they say net ATP, or even if they just say how much ATP do you get from glycolysis, please say 2, okay?
You will want us if you say something different?
Yes,
I know.
yes, I will. And that process of making ATP, directly from the chemical reactions, what's that called when you make ATP that way? It's kind of a mouthful.
I'm sorry,
When you make ATP directly from the chemical reactions, that's called substrate level phosphorylation, okay? So during glycolysis, you make 2 ATP from substrate level phosphorylation. However, what do you also generate during glycolysis that you'll be able to use later on to make more ATP?
NADH.
You generate NADH, which is like this, a temporary electron carrier that you can then feed into the electron transport chain later on. Where in a cell does glycolysis happen? Cytoplasm. So you don't need mitochondria to do glycolysis. All right. At the end of glycolysis, you'll have these 2 pyruvic acid. Now, what becomes of the pyruvic acid if you don't have oxygen? They become lactic acid, okay? But if you do have oxygen, what becomes of the pyruvic acid? They get converted into what?
Acetyl-CoA.
Acetyl-CoA, right? Acetyl coenzyme A. And then the acetyl-CoA is going to enter into the Krebs cycle, right? What's the first substance you make when you enter into the Krebs cycle? And it's also the name for the cycle? The first thing you make is citric acid, right? If you have 1 acetyl-CoA and it goes through the Krebs cycle, how many ATP do you make from 1 acetyl-CoA going through the Krebs cycle? 1. But assuming you started with glucose, how many acetyl-CoAs are you going to have? 2. They're each going to go through it. So to answer that question, if somebody asks, like me, how many ATP do you make directly from the Krebs cycle, you should say 2. Okay? So it's 2 and 2. Pretty easy to remember. 2 from glycolysis, 2 from the Krebs cycle. And again, that, because you're making it directly during the chemical reactions, they classify that as substrate level phosphorylation. Bless you. But once again, just like with the glycolysis, what else do you make that's going to give you more ATP later on? You make NADH, and you also make FADH2 that you can use later on. Okay. Where inside of a cell does the Krebs cycle happen? Matrix of the mitochondria, which is like the innermost place of it. Okay. Then lastly, you finally have the electron transport chain. Where does the electron transport chain happen? On the inner mitochondrial membrane, which is the thing that kind of forms those little folds called cristae. And it's going to involve proteins that are embedded in the inner mitochondrial membrane. What's the name of those proteins? Cytochromes, right? And so what's going to happen is the NADH and the FADH2 from the other steps, they're going to show up in the matrix, and they're going to drop off their electrons to the cytochromes, and then they're going to drop off their hydrogens kind of into the matrix, right? The electrons are going to be passed from one cytochrome to the next cytochrome to the next cytochrome, and as that's being passed, that is generating energy that's going to run a little hydrogen pump that's in the membrane, and that pump is going to pump the hydrogens from the matrix into the space between the membranes. Pretty soon, hydrogen builds up, and you've created a gradient, And now the hydrogen would like to come back into the matrix because there's no hydrogens there anymore. The only way for it to do so is to pass through this little stupid channel called ATP synthase, and as it passes through there, what's created? ATP, right? As you go through, the energy of motion of the hydrogen is used to attach a phosphate group to ADP, and you create ATP. What ultimately becomes of the electrons and the hydrogens? They get attached to what?
Then they get converted to water.
Oxygen. They get picked up by oxygen, which then creates
I think so.
the water, right? The metabolic water. Okay, so remember, oxygen is the final acceptor of the electrons and the hydrogens, and when it does so, it forms this metabolic water. And how much metabolic water in a 24-hour period? 200 milliliters. Okay. Good. Looks good. Other fun facts. Don't forget that vitamins B2 and B3, which are riboflavin and niacin respectively, are needed to make FAD and NAD respectively. So for the big math, for the big picture math, assuming you start with one glucose, how many, and you have oxygen, so you can go through all the steps, how many total ATP do you make? 36 or 38, and the way that breaks down is 4 ATP coming from substrate level phosphorylation during glycolysis and the Krebs cycle, and then 32 or 34 ATP coming during the electron transport chain. What's that method of ATP formation called in the electron transport chain? Oxidative phosphorylation. Okay, good. All right, looks pretty good. All right, so other types of carb metabolism that we talked about. What's it called when you store up extra glucose in your liver in the form of glycogen?
Glycogenesis.
That's glycogenesis. So forming glycogen is referred to as glycogenesis. And what hormone promotes glycogenesis? Well, what's the I've just eaten hormone? Insulin. All right? Remember, insulin helps glucose to get into your body cells to feed them, but it also helps any extra glucose to be taken up by the liver and converted into glycogen. And it also helps any extra glucose, unfortunately, to also be taken up and converted into fat in your fat tissue, right? All right. When you haven't eaten in a while and you're in that post-absorptive state, you got to keep glucose levels up. What's it called when you break down glycogen? Aren't these terrible G words? Glycogenolysis, right? And that's going to be glucagon and then also epinephrine. They stimulate glycogenolysis, okay? And then lastly, one other way to raise blood glucose levels is to make glucose starting with a non-carbohydrate, like an amino acid or a fat. And what's that process called when you're starting from a non-carb and making glucose?
Gluconeogenesis.
That's gluconeogenesis. Once again, our friend glucagon helps with that. But then also, who's the other guy that promotes gluconeogenesis? What's your stress hormone? Cortisol, right? And that's actually one of the reasons why cortisol really sucks after a long period of time, right? Cortisol will promote the breakdown of muscle tissue just to create glucose for you, and it starts to suck, okay? Lipid metabolism, what's it called when you form lipids? It's called lipogenesis, and when you break down lipids, it's called lipolysis. Lipids have problems being transported in your blood. Why? Lipids are hydrophobic, the blood's mostly water. So how do you have to kind of trick the blood in order to transport the lipids around? Put them in these things called lipoproteins, hide them inside there. It's like contraband or like, smuggling drugs. Anyone ever smuggle drugs into a country? All right, extra credit for that too. Extra credit if you get berry and you smuggle drugs in at the same time.
Very, very bad.
Okay. What's the good kind of cholesterol?
HDL.
HDL cholesterol. What's the bad kind?
LDL.
LDL cholesterol. Okay, lipogenesis is fat synthesis. Again, insulin not only promotes glycogenesis, it also promotes lipogenesis, unfortunately. Lipolysis is breaking down fats. And again, when you break down like a triglyceride, you separate the glycerol backbone from the fatty acid chains, and you can use the glycerol and feed that into the glycolysis and make ATP that way. As you break down the fatty acid chains, you break off 2 carbons at a time. That's called beta oxidation. And you form acetyl coenzyme A, which can be fed into the Krebs cycle to make energy that way. Unfortunately, if you do that too quickly, acetyl-CoA starts forming what? Ketone bodies, which can acidify your blood and potentially cause problems that way. Did I mention diabetics?
No, not
Ooh,
directly.
I sort of dropped the ball on this. So, for people that go like on a low carb diet, they get a ketogenesis. It's not usually a big deal. They don't really acidify their blood that much. But an uncontrolled diabetic, somebody that's not taking their insulin or is not taking their meds, they can't get glucose into their body cells. So those individuals, their body kind of freaks out and it starts breaking down fats really rapidly. And they can get severe ketogenesis happening. And there's a problem, it's called diabetic ketoacidosis, where these ketones build up and it significantly acidifies their blood and can actually cause like death and other problems. So it can be a big deal, but like in your typical person that's on like a low carb diet or something, it's usually not really an issue. All right, 3 key molecules at the metabolic crossroads. What are the 3 key molecules? Pyruvic acid, acetyl coenzyme A, and then glucose 6-phosphate. 5. 2 metabolic states that you have during the day. You're either absorptive or you're post-absorptive. That's it. Your whole life is just boiled down to either eating or wanting to eat, okay? So the absorptive state, you've just eaten. The key thing with the absorptive state is to make your cells happy, give them the glucose that they need at the moment, and then any extra glucose, store it up for future use, all right? By converting it into either glycogen or into fat. Again, when you hear absorptive state, think insulin, okay? Post-absorptive state, the trick is to keep glucose levels up. Why do who wants the glucose levels to be high? Like your brain or the red blood cells, they like nice high glucose levels. Here, think glucagon. Glucagon promotes glycogenolysis. It promotes gluconeogenesis. Both of those things help to keep your blood glucose levels up. Basal metabolic rate is basically the rate that your body's kind of undergoing these chemical reactions, breaking down glucose to make ATP, etc. when you're at like rest or in a quiet fasting condition. There's a strong association between the metabolic rate and your body temperature. As the metabolic rate goes up, your body temperature goes up. What's the normal value for your core body temperature in Fahrenheit? 98.6 degrees Fahrenheit. What is it in Celsius?
37.
37 degrees Celsius. Just remember, peripheral tissues can be lower than that, right? 1 to 6 degrees lower, centigrade lower. Metabolically active organs, like your skeletal muscles or your liver, they're kind of like the furnace of your body. They generate a lot of the heat. Then it falls on your skin, mostly, to control heat loss. What was the method of heat loss called where you radiate heat off to something cooler in the environment, but that's not in direct contact with your body? Thermal radiation. What is it called if you are in physical contact with something cooler?
Conduction.
That's conduction. What's it called when you move a gas or a fluid across your body and draw the heat away that way?
Convection.
Convection. And then the last one, of course, is evaporation, where you convert a liquid into a gas, and that gives off heat that way, and that's what you do when you sweat. Okay. What are some of the body changes that you'll do if you start overheating? If you start to run hot, what body changes will you do to try to cool you off?
Sweat.
So you'll sweat, sure. What else?
Dilation.
You'll dilate what? The blood vessels that go close to the surface of the skin to try to give off heat that way. What else would you do? Shut down what hormones? What's the
T3 and
hormones that
T4.
increase? What's that?
Is it T3 and
Yeah,
T4?
shut down T3 and T4. You want your metabolic rate to be as low as possible so that you don't generate heat, right? And then obviously, if your body temperature was too low, you just do basically the opposite of all those things. And you might also shiver, right, in order to generate more heat. All right. Nutrients, substances that your body needs for growth, maintenance, repair. 6 main nutrients: water, carbs, lipids, proteins, minerals, vitamins. Vitamins and minerals are very similar. They both tend to work along with enzymes to help turn enzymes on in your body. When it's a mineral that's working with an enzyme, you call it a cofactor. When it's a vitamin that's working with an enzyme, you call it a coenzyme. I think this was mentioned before, but chemically speaking, what's the difference between minerals and vitamins? Minerals are inorganic, vitamins are organic. Also, minerals can be found in the Earth's crust, right? We all established that. Vitamin deficiencies. When you don't have enough vitamin C, what's that problem called? Scurvy. What's the protein that you can't make when you have scurvy? Collagen, okay? And you get bleeding gums, mouth ulcers, all kinds of other problems. I mentioned beriberi before. What does that come from? A deficiency of
Thiamine.
B1. What type of rice should you not eat?
White.
White rice. We're hating on the white rice. Don't eat polished rice, polished or white rice. It doesn't never say polished on the label, right? It just says white rice.
Yeah.
It doesn't say polished anywhere. All right. Because polished sounds like a good thing. Like, wouldn't you want your rice to be polished, right? No one wants like tarnished rice or like dirty rice. Would you like some unpolished rice? No, thank you. Sorry. I'm getting everyone confused. All right, let me keep rolling. Obesity. What's our definition that we're going to roll with for test purposes? 10 to 20% above the desirable level because of too much fat tissue, right? Too much adipose tissue. What's the healthiest state in the United States, at least as 2007?
Colorado.
Colorado. What are the least healthy states? Alabama,
Tennessee.
Mississippi, and Tennessee. All right. All right, any questions about any of this stuff? Okay, good luck. If you have any questions, shoot me an email. Have a nice weekend, all that stuff. Thank you.
Oh.
I hope you have that.